Hello everyone, my name is Dr. Colin Campbell and I'm a senior research scientist here at Meter Group. And for today's Chalk Talk, we're going to be talking about modeling vertical variation in temperature. On the left, I've put together a graph that shows the maximum and minimum temperature with height and depth in the soil at some snapshot in time at a particular place. And it's interesting to note that the change in temperature with depth in the soil is much faster than the change in temperature with height, whether we're talking about a maximum or a minimum. And the reason that is that even though air is a good insulator, it also mixes really well. And that mixing is caused by eddies. Well, and there's a little more to that story. It depends specifically on surface heating by the sun through radiation, the cover type, whether it's plants, rocks, boulders, just straight soil, snow, anything like that, and also wind. And so if we were going to model that, we would start by writing an equation that at temperature, at sun height z above the surface, and our variables are there noted below here, that's equal to an aerodynamic surface temperature T0 minus the sensible heat flux divided by 0.4 times rho Cp, which is the volume-specific heat of the air, times a variable called U star, which is the friction velocity. Now we multiply all of that by the logarithm of z, the height above the surface, minus d, which is the zero plane displacement, divided by zh, which is a roughness parameter. Now you might notice up here in the list of variables that the zero plane displacement is right here. It's 0.6 times 8. H is the canopy height in meters, so that's 0.6 times h. The roughness parameter can be estimated too as 0.02 times the canopy height, or times h. So now we have an equation that will help us model temperature with height. But one of the problems is often we don't know things like h, our sensible heat flux, and U star, our friction velocity. One of the things that we notice about this equation that's interesting is that it's set up somewhat like a linear equation. Well, you know a linear equation is just y equals mx plus b. Well, this isn't written quite that way, but if we look closely, T0 could be b minus h over 0.4 U star Cp, rho hat Cp U star. This could be our m, and this value could be our x. And if we do that, we actually can get a little use out of graphing temperature with height. So we went out one day and measured this. And this is a key part of this. You need a meter group set of sensors set up at certain heights above the surface. Here we did 0.2, 0.4, 0.8, and 1.6 meters above the ground. And just to visualize this nicely, if we graphed height here and temperature on the x-axis, this is what it looked like, not unlike that graph I showed you above. I do this just so you can visualize the temperature with height, but we know that from this equation that these two things should be switched because temperature is the dependent variable over here and height is the independent variable over there. And so let's show a graph that does that. So let's drop down here. This now is graphed in such a way that it is graphed with the independent variable on the x-axis here in height, and this is our y over here. So if we fit this curve with today's calculators, it would be actually fairly easy to get a curve that would fit that. But since it's a linear equation, we can drop down here a little further, take this and this, and graph those guys together. So here's the graph of what happens when we do that. So here's the log of z minus d over zh, and here's temperature with height. And you notice, just like we suggested, it creates a linear equation. So the equation that we have here is y equals minus 2.0, and I don't know, significant figures, maybe 2.01 times x plus 34.5. Well, what we learned above is that from this equation, this B value was equal to T0, our aerodynamic surface temperature. So our surface temperature is 34.5 degrees. So we can estimate what the temperature is down here at the surface, even though we only measured down to right there. M value here, M, that's equal to negative 2.01. Now, if we look at the equation, our slope value here, that M, is equal to negative H over 0.4 U, or rho hat Cp U star. So this is equal to negative H over 0.4 rho hat Cp times U star. Now, if we were interested in something like the sensible heat flux, which we often are, we can simply rearrange this equation to say H is now equal to negative 2.01, and then we transfer the other negative to the other side, that guy right there. Okay, and then we're going to multiply by 0.4 rho hat Cp times U star, and up here I gave you values for some of the, for specifically, oh, I didn't put that in. It's actually for air temperature of 20 degrees C, this is about 1200. And the units on that I've specified there, joules per meter cubed per C. And so if we put that in, a typical unit for this, and it should be measured in the field over the specific canopy you're in, is about 0.2, and the units on there, as you'll see if you look back in the video, are 0.2, they're meters per second. So if we did this calculation, actually we learned that there's about 193 watts per meter squared of sensible heat flux coming off that surface. So if we can measure temperature at a few heights, we can actually estimate what the heat flux is coming off the surface, assuming we know something about our canopy. Thanks for listening.